Hello and welcome back to another Calculus 3 multivariable calculus video. Today we're going to be going over general change of variables. So I guess the question of what is a general change of variables? Well, we've been doing this all along realistically. What we're essentially doing is we're changing variables to make an integrand or an integral simpler. Like I said, this sounds a little bit repetitive since I've made a couple of videos on us changing variables, but the reason I really like this section is because it kind of explains the why and the how we're doing it, right? So why are we doing it? I just said is to make the integrand in our integral simpler. You could kind of think of it like U substitution that we did in Calc 1, Calc 2, and even Calc 3 we've been doing U sub. You can kind of think of it that way. It's pretty similar. Perhaps the variable is more similar than we know quite yet, but that's pretty much what we're going to be doing and why. So I guess the question is how. Essentially, when we're doing general change of variables, well, we're going to be finding a transformation t relating xy variables to uv variables. What am I trying to say here? Well, essentially, we're going to be given and or sometimes we're going to have to find a transformation t, like the one given here. Well, we're going to have some t where we have an x is equal to some function of g of u of v. And similarly, a y wherein our y is a function of u and v. Basically, our x and y coordinates are going to correlate to these uv coordinates by that transformation. So we're going to be changing our coordinate system manually, kind of. Instead of we're going to be showing the work, and it's mainly going to be parallelograms as we'll see today, but really we've been doing this all along, like I said, so I guess we should just get into a familiar example here. Well, what is our familiar example? Well, say we have the double iterated integral of e to the 1 minus x squared minus y squared dy dx over these bounds. Well, how are we going to make this easier? Well, maybe we're familiar with this already. Well, that x squared minus y squared, well, that can just be written as 1 minus r squared. And we're basically going to be able to convert this into, well, polar. So converting this into polar, we're going to be using a transformation. And although it hasn't been explicitly stated quite yet, that's what we've essentially been doing all along. Well, our transformation t is our x is equal to r cosine theta and our y is equal to r sine of theta. These are two functions in r and theta, and we're going to be using those to convert our x, y to r theta. So when we do that and we undergo that transformation, well, we have this new iterated integral with different coordinates, with different variables. So basically what I'm trying to say here is changing variables will make the integrals and the integrand easier, as we've seen. So one of the other really nice reasons I enjoy this section is because we kind of get an explanation finally on why we have this r in our dr d theta, and similarly why we may have that rho squared sine of phi in our spherical coordinate transformation. It's very interesting, and I won't get to that until later in the video here, but I guess the question is, we have two key questions whenever we're doing these kind of transformations, this general change of variables. Well, first question is, what is s is equal to transformation of r? So basically what this is saying that, well, if we're transforming these graphs, these functions, into something easier, well, how are we going to find that? How are we going to find our s is equal to tr? And spoiler alert, we're pretty much just going to be using simple algebra given that transformation, given functions and or points in our graph that was given, and we can essentially graph something new, something more digestible perhaps, especially in a parallelogram sense. And secondly, what is our dA going to be? So we know that the definition of our integral has that some kind of, our double integral, has some kind of dA, dy dx or dx dy. Well, what is that going to change into? I kind of said it a little bit earlier, but this kind of explains why we have that r dr d theta, or that rho squared sine of phi. Very interesting stuff here. And the other interesting thing about this section is that, under transformations, we're essentially doing linear algebra here. And that's kind of why I like this section so much. It's because it's a really breath of fresh air, in my opinion. So I guess let's go ahead and just get into our first example here. First example states R is a parallelogram in the xy plane with vertices 0, 0, 0, 1, 2, 4, 2, 5. Find S is equal to TR, where the transformation is x is equal to 2u and y is equal to 4u plus v. So I already took the liberty of graphing this out here, and it looks like we have a parallelogram here. Well, what is this? What are the slopes on these all? Well, okay, I color coordinated a little bit. Well, this right here, this purple section right here, well, that's just going to be, what is that? That's going to be x is equal to 0, right? And yeah, there are bounds on it very technically, but in a very general sense, this is x is equal to 0. Similarly with this green bit, well, we have our 2's right here, so then we can just identify this as x is equal to 2. And as for our slopes over here, well, this is a linear slope, so we just kind of have to figure out exactly what that slope is. Well, what is that probably going to be right here? Well, if we just go ahead and do, what is that, 4 goes up, y is equal to 2x here. And kind of proving that, well, what is our input for right here? Well, if we plug in x is equal to 0, y is also going to be 0. That checks out. If we plug in x is equal to 2, well, what's the output there? It's going to be 2 times 2. That's going to be equal to 4. Well, that checks out as well. Similarly with this blue bit, well, this is like the exact same slope, just translated up one. So it looks like this is just going to be y is equal to 2x plus 1. So I guess the procedure here is spoiling it a little bit. I think the easiest way to do this is to make a table here. Well, what do we have in our leftmost part of the table? We have the xy plane. What are we going to have in the xy plane? Well, these can either be coordinates from our xy plane or they can be slopes, equations from our xy plane. In this case, we're definitely going to be doing equations. So what are our equations in the xy plane? Well, we already just solved those. Well, we're going to have some x is equal to 0. We're going to have some x is equal to 2. And you'll find that I really enjoy color coding whenever I am doing these. We're going to have y is equal to 2x right there. And then we're going to have y is equal to 2x plus 1. Well, the question is now, how are we going to transform our xy plane into the uv plane? Well, we're going to be using that transformation that we were given over here. Our transformation is x is equal to 2u and y is equal to 4u plus v. Well, let's just go ahead and write that down. Instead of having that right there, well, we're going to have that x is equal to 2u and that y is equal to 4u plus v. Okay, what are we going to be doing here? Well, as for our x coordinates, that's going to be pretty self-explanatory. We're going to be plugging in x is equal to 0 for this first instance. Well, if we plug in x is equal to 0, then we have 0 is equal to 2u, meaning the only solution for this, we'll simplify that later. We're going to have 0 is equal to 2u. And similarly with our x is equal to 2 equation, well, we're going to have 2 is equal to 2u. Just plugging those x values right here, right into that. And perhaps a little bit more complex, maybe, but what are we going to be doing for this one? Well, we're going to be plugging in 2 of our transformations. We're going to be plugging in both. So what are we going to be plugging in? Well, our left side, so our y, we're going to put that to be 4u plus v, okay. And our right side is going to be 2 times our x, which is going to be 2u. So writing this down, we're going to have 4u plus v is equal to 2 times our transformation over there, 2u. And very similarly, in fact, only with one difference, I guess. We're going to be doing the exact same thing over here when we plug in our transformations. 4u plus v is equal to 2 times 2u. And then obviously we're just going to have that plus 1 there. And then this third column that we got going on here, well, that's just going to be me simplifying this. Well, how can we simplify these further? Pretty easily. Well, the only solution for this equation right here is going to be u is equal to 0. Okay, well, what's the solution here? Well, if we divide 2 out by both sides, well, that's just going to be u is equal to 1. Okay, a little bit more algebra heavy here. Well, we have 4u plus v is equal to 4u. We subtract that 4u out, well, that's just going to be 0, right? So we're going to have v is equal to 0. And kind of similarly over here, we're going to have some 4u plus v is equal to 4u plus 1. Well, if we subtract that 4u out, we're going to have v is equal to 1. Whereas over here, we subtracted that 4u out, v is equal to 0. Okay. This looks a lot more digestible. Was the other one difficult already? Perhaps not. Obviously subjective for sure, but we're just going to go ahead and graph this really fast. Well, our u is equal to 0. Our u correlates to our x-axis. Well, our u equal to 0, we can just go ahead and draw a straight line up from there. Our u is equal to 1. Similarly, we're just going to go ahead and draw a straight line up from over here. Let's label these. U is equal to 1 and u is equal to 0. V is equal to 0. Well, that's just going to be this line right here connecting them. Similarly, v is equal to 1 is just going to be this line connecting them as well. And this right here is going to be our new region, S, wherein our S is equal to TR. So that kind of answers our first question here. I'm going to get into one more example after this just so we can really hammer in this idea, and maybe we can use a different method to find our transformations here because they're not always going to be so straightforward as plugging in x and y, right? They're not always going to be so straightforward as to that. We got pretty lucky on this one, and of course it was by design, but as you can see here, this kind of parallelogram that we have in the xy plane, well, this might have been a little bit more difficult to integrate if we were given something like that. Well, using that transformation, we got a rectangle, we got a square, a rectangle. This is going to be a pretty easy parallelogram if we were to change our bounds, right? So jumping the gun a little bit right there, I guess, but that is obviously making this transformation right here, it really did make this parallelogram a lot more digestible in the UV plane. And we will be using that little graph method more in the future. Okay, let's go on to our next example here. R is the region in quadrant 1 bounded by x is equal to y squared, x is equal to y squared minus 4, x is equal to 9 minus y squared, and x is equal to 16 minus y squared. Our transformation is given as u is equal to x minus y squared, v is equal to x squared plus y squared. Find s is equal to the transformation of r. So it's asking us for the exact same thing here. Well, we have definitely more complex functions here, and as we can see, this parallelogram that we got going on is pretty curvy. That's interesting for sure. We already have the x, y coordinates here, or the functions, I guess I should say. And like I said, I like color coding these so that we can see exactly what correlates to what. As I did in the last example, well, this correlates to that, this correlates to that, this correlates to that, and this correlates to that. I kind of enjoy doing that, like I said. It makes it a little bit easier on the eyes and understanding exactly, well, what transformations did what exactly. So I guess starting off here, well, let's go with our easiest function, arguably. We already have our functions, like I said, so we can just write them down. X is equal to y squared. And kind of doing something similar, we're just going to write down our x is equal to y squared, and with that transformation of up or down, 4. Up 4. Next, we'll write this one. And finally, our green function. Simple enough. Okay, well, how are we going to turn this into the UV plane? We're going to be using our transformation here. U is equal to x minus y squared. And v is equal to x squared plus y squared. Okay. So, in the UV plane, how are we going to convert our xy plane into the UV plane? Well, we could rearrange, for sure, we could rearrange this into x is equal to u plus y squared, and then we would have to plug that in, and we would also have to inversely do y squared is equal to x minus u, but there's really a simpler solution here, and maybe you're already seeing it. Well, our transformations look pretty similar to what we're already given here. Why can't we just rearrange our functions into our transformations, right? Well, we have x is equal to y squared, and our transformation of u is x minus y squared. Well, why don't we just subtract that y squared out, and we're going to be given x minus y squared is equal to 0. Okay, well, we can really just do that all around, right? Well, if we just subtract that y squared out right here, well, then it's going to be the exact same thing, but it's going to be equal to something this time. We're going to have x minus y squared is equal to negative 4. Okay. Similarly, well, we have some x plus y. Oh, well, this is actually not right. Sorry. Well, similarly, if we just add out that y squared, well, that looks an awful lot like our v transformation as well. Well, what do we do here? Well, why don't we just add that y squared out? X plus y squared is equal to 9. Similarly, over here, add this y squared out. It's going to be x plus y squared is equal to 16. Okay. Well, we rearranged our xy equations to kind of conform to our transformation, meaning our transformation is going to be pretty easy now. Well, this is just going to convert into u, these two. These are going to convert into u, and these two, it looks like these are going to convert into v. So if I just plug in that u is equal to x minus y squared right here, well, we get u is equal to 0. Okay. We get u is equal to negative 4. We get, let me use the right color here. We get v is equal to 9. And we get v is equal to 16. So essentially rearranging our functions in the xy plane to conform to that transformation may make things easier. Simplifying, there's not really much to be done here, but I'm just going to write it down anyway. U is equal to 0. U is equal to negative 4. V is equal to 9. And V is equal to 16. So I guess this kind of talks about, well, we have two ways that we can transform here. First of all, I guess what we were doing prior is we could solve for t in x and y, and then we could sub in, right? So we could have solved in this first example, for example, I talked through it briefly, but we could have solved in this transformation right here for x, and we could have solved it for y, and we could have set it equal to each other, and we would have gotten the same answer. It would have been uglier for sure, but we would have gotten the same answer eventually. But why would we have done that, right? Why would we do that if we can just do the alternative, which is rearrange our xy equation, right? If we just rearrange our xy equation, then we're going to just be able to transform that u into v, u and v pretty simply here, and I demonstrated that there, but just because why would we brute force our way through it if there's just an easier way to do that? So I guess the moral of the story is here, at least, well, what should we do? What we should do is, well, we look at our transformation and we look at our xy plane functions. Well, we need to think, will I get those transformations easily if I just rearrange my xy equation? And if the answer is yes, then you should absolutely go about doing that. Otherwise, you will have to brute force it. We'll have to solve our transformation for x and y, and then we would have to sub it in ultimately. So yeah, that is how we do that. Now let's go ahead and graph this. Well, u is equal to 0. That's just going to be this right here. We don't know what it looks like quite yet. U is equal to 0. U is equal to -4. Excuse the butchered kind of scale I'm going to be using here. I always use bad scale. This is u is equal to -4. This is u is equal to 0. Okay. Well, what are our v looking like? V is equal to 9. And v is equal to 16. Looks like we're going to have just a square here, a rectangle. V is equal to 9, and v is equal to 16 will be up here. Well, would you look at that? We have a much easier kind of region right here to integrate over compared to that region right there. So I guess this was more of a motivating example on why we'll definitely need to use transformations in order to make things easier. Yeah, like I said, this green kind of 16 minus y squared correlates to this v is equal to 16. This blue u correlates to this u is equal to 0. This purple x is equal to y squared minus 4 correlates to this line right here. And then finally our kind of orange yellowish function correlates to this right there. As you can see, this is why I kind of enjoy making the colors kind of pretty. So I guess moving on, we kind of answered our first question of how do we find S, our new domain S, is equal to the transformation of R. Well, we pretty much procedurally, just to go over really fast, well, we graph and we draw our original, our R region, or whatever region is given, and using our transformation in a graph, or in a table, excuse me, we're going to be able to regraph our function into something a lot more digestible in the UV plane. So the question is, what do we do with our dA now? Well, I want to start off by recalling something, and perhaps this is new to some of us. Well, given a 2x2 matrix, as given here, well, the determinant of that 2x2 matrix is going to be what? Well, it's going to be something that we're familiar with. It's going to be this kind of barred determinant right here. I can't really come up for a word here, where we have the exact same thing, right? And what are we going to do to solve for this 2x2 determinant? Well, we're going to multiply this a value by this d value given right there, and we're going to subtract it by this b value multiplied by this c value. This is something that we did with cross product in the 3x3 matrix, that is, yes, but it is something that we did with cross product in calculus 2, if we can recall. But in 2x2, it's essentially the same procedure here, just multiplying that AD minus BC, and that's just something I kind of want to recall really fast, because this is going to be important when we are calculating our dA. And what do we do with our dA? Well, we're going to need to know the determinant. The determinant of what? Well, our definitionally here, well, we're going to be given a transformation. X is equal to some function in u and v, and y is equal to some function in u and v as well. We're going to be using the Jacobian. So I guess the question is kind of, what is a Jacobian? Well, a Jacobian is essentially a partial derivative determinant, right? So, well, we have our partial of x with respect to u right here, and our partial of x with respect to v right here. And then similarly on the bottom, we have our partial of y with respect to u and our partial of y with respect to v. Well, we're going to be doing the exact same thing that we're doing with this a, b, c, d determinant over here. Well, we're going to be doing this partial of x with respect to u multiplied by this partial of y with respect to v minus this partial of x with respect to v and this partial of y with respect to u. So that's what a Jacobian is, and I guess the question is, why are we using a Jacobian? Well, to put it simply, the Jacobian, it's going to be a scaling factor whenever we're doing this. I guess we'll get to that theorem in just a little bit, but it's going to be a scaling factor. What this means is when we're transforming some kind of region, it's going to get stretched and compressed. Well, how do we account for that stretching and compressing? Well, this is going to be determined by the Jacobian. The Jacobian is a local scaling factor, meaning if we didn't include our Jacobian when we are computing our integral, well, we don't have to solve for the Jacobian when transforming our S into, or our region R into S using our transformation. We didn't have to do anything with the Jacobian, but when we are going to be integrating, well, if we don't integrate, then, and we don't multiply our integrand by that scaling factor, the Jacobian, then we're gonna get our integration results wrong. So I guess that's pretty much, I would say that's a fair explanation of what the Jacobian is. Just one more little statement about it is it's pretty much the Jacobian. It tells us the area of a new parallelogram in the UV plane, right? So if we're graphing a parallelogram in the XY plane and we map it to the UV plane using our transformation, the parallelogram is going to be warped. It's either going to be stretched, or it's going to be compressed, or it's going to be somehow messed with because of that transformation. And the Jacobian tells us the area of our new parallelogram in that UV plane. Once again, just think of it as a scaling factor when we're transforming. So I guess getting into our theorem here, well, given a double iterated integral of f of xy over the region R and a transformation, well, we can just rewrite this double iterated integral of f of xy over R as the double iterated integral of our function in u and v variables multiplied by the absolute value of the Jacobian, or the multiplied by the absolute value of that scaling factor over the region S. So what we're pretty much going to be doing when we're integrating here is we're going to be transforming our integrand into u and v, and we are going to be having our region S. Now, like we said over here, I was kind of spoiling it up here, where our x and y variable, well, this was going to be, these two were going to be our regions if we were given integrals there, whereas using our transformation, well, these two are going to be our S regions. So that's pretty much that, and then once again, that is going to be multiplied by the absolute value of the Jacobian. Very important. It needs to be the absolute value of. So I guess one more thing to kind of say about this is, well, I guess to sum it up, well, we're going to have a new bounds of integration. We're going to have new limits of integration there. We're going to have a new integrand right here in terms of u and v. And then, like I said, this Jacobian is just going to be our absolute value of our scaling factor. And the reason I think that the Jacobian is so interesting is because, well, it kind of explains why we have that r dr d theta, right? Well, our dA is going to be dr d theta, but if we took the Jacobian of our transformation, x is equal to r cosine theta, and x is equal to, or y is equal to r sine theta, then that is going to be our r. That r is what pops out of the Jacobian. So it kind of explains why we had that r dr d theta, which is extremely interesting. I didn't prove it earlier, and it obviously can be proved as well by just like multiplying, well, it's just kind of like proving that polar rectangle, summing all of the little rectangles within that polar rectangle. I'm going in a rant here, I apologize, but it could be proved in another way, but the Jacobian does the exact same thing. It's a scaling factor. So the scaling factor within our r theta, our polar coordinates, was r. So I guess that's our theorem. So kind of getting into our last example here, we're asked to evaluate the double iterated integral of the square root of 2x times y minus 2x dA over the region R, where R is a parallelogram in the xy plane, given the vertices 0, 0, 0, 1, 2, 4, 2, 5, and our transformation, x is equal to 2u, y is equal to 4u plus v. So I guess the reason I didn't really do this again is because, well, we already did this in a prior example up here. We did this already. So I guess kind of skipping all this right here, we already did all this. we were given, in the end there, we were given u is equal to 0. We were given u is equal to 1. No, sorry. U is equal to 1. And the green, sorry. I guess it's kind of a downfall. I can't just use whatever color I'm on. V is equal to 1. And finally we had V is equal to 0. And we kind of had this region S right here. From that transformation, from our region R over here. Okay, well, how are we going to evaluate this using our transformation? Well, what are we going to do here? We're going to first of all, we have to transform our integrand here. Well, what is our integrand as is? Our integrand is the square root of 2x times y minus 2x is our integrand as of right now. So I guess we have to kind of use our transformation there in order to make it so our integral is solvable. So we're pretty much just going to be plugging in our x and y here. So using our x is equal to 2u, we're going to now, I'll write the square root. Using our transformation, we're going to have 2 times 2u multiplied by 4u plus v minus 2 times 2u. I'm just going to write that as 4u. Square root of that. Simplifying this a little bit, well, we're going to have the square root of 4u, and that 4u minus 4u cancels out, so this is going to be times v right here. So our new integrand looks like it's going to be the square root of 4uv. Okay, well, what's our next step? According to our theorem here, well, we have our region S. We're given right here. We already did that. We just transformed our integrand here. That's going to be the square root of 4uv. Well, what's next? We're going to have to solve for the Jacobian now. Kind of spoiled it right here, I suppose. Well, what is our Jacobian? Well, recall that our definition for a Jacobian is the Jacobian of u and v is equal to the determinant of the partial of x with respect to u and the partial of x with respect to v, as well as the partial in y with respect to u and the partial of y with respect to v. Taking the determinant of that, oh man, that's not going to hit, huh? Okay, well, how are we going to do this? Well, we're pretty much going to be using our transformation. How are we going to... We don't really... conveniently enough, our x and y, they're already in function of u and v here. So we really don't have to do much. We're going to have x is equal to 2u and y is equal to 4u plus v. So pretty familiar with what we're used to here. Well, what's the partial of our x function with respect to u right here? Well, it's going to be 2. If we take the derivative of that, it's going to be 2. What's our partial with respect to v? Well, there is no v value in our transformation right here, so this is just going to be 0. Oops. Okay, similarly, well, what's our partial of y with respect to u? Well, we have that 4u right there. That v is treated as a constant. Therefore, we're going to be taking the partial of 4u plus v with respect to u. That is going to be 4. Similarly, partial of y with respect to v, well, that's the v right there. The 4u is treated as a constant. Therefore, this is just going to be 1. So using our kind of determinant over here, AD minus BC, how are we going to do this? Well, we're going to do 2 times 1 minus 0 times 4. So this is going to equal 2 times 1 minus 0, which is going to equal 2. That is our Jacobian. So just setting up our integral here. Well, what are our bounds? Oh, yeah, let me rewrite this. Okay. Well, our new integrand is 4uv, the square root of 4uv. The absolute value of our Jacobian is going to be 2, make sure you always write that absolute value, just so in case we're on an exam and there's graders, well, if you have a negative, there's supposed to be a negative there, well, they might dock you for points. Let's just say that. So I guess don't let yourself get messed up by not having that absolute value bracket. Regardless of what we do, it's pretty much going to be around simple, and honestly, it's going to be the exact same considering our bounds are 0 and 1, 0 and 1, as we can just see there. So we'll just go du dv. Well, what are our bounds on our u integral? Well, it looks like it's just going to be from 0 to 1, as we can see right there. There's not really much to write here. It's bounded by 0 and 1 both ways. So this is going to be our integral that we will be solving right here. That is general change of variables. Overall, what's the kind of takeaway here? Well, the kind of takeaway is we're essentially doing linear algebra here, but we're doing calculus with it now, I suppose. Definitely very interesting. Jacobian is definitely something that is certainly interesting whenever we're talking about our transformation when we were doing xy to polar coordinates. That's certainly interesting, and it kind of proves why we had that r d theta, although I will not be proving it here. Yeah, if we evaluated that, then that would be our f of uv. Thank you very much.